In this video, we'll take a look at a few more recognizable properties and prove that they're recognizable. So the first one we'll look at is we'll prove that every regular graph, not just that regularity is a recognizable property, which is a consequence of Theorem 9.7. I'll remind you of Theorem 9.7 that we can recognize the order, size, and degrees of the vertices. So in particular, if all the vertices have the same degree, then it's regular. If not, then it's not regular. We can recognize that because we can recognize the degrees of the vertices. So regularity is a recognizable property, and actually a lot more can be said. That is that every regular graph of order at least 3 is actually reconstructable. And so this class of graphs are all reconstructable. So let's take a look at a proof of that. How can we prove that every regular graph is reconstructable? Well, the idea is not too difficult here. So since we can recognize that it's regular, we can assume without loss of generality that G is an R regular graph. So we can assume G is an R regular graph, since regularity and degree of regularity are both recognizable. Okay, so we have an R regular graph. So what that means is that what we need to show is that we can determine G from all of the G sub i's. So again, we'll let G sub I equal G minus V sub I, and we want to determine G from this set of vertex deleted subgraphs. So let's just take a look at G1. So the order of G1 is n minus 1. So G is our regular, we'll say order n at least 3. Order of G1 is n minus 1. And let's see, so R vertices, since V1 was adjacent to R vertices in G, G sub 1 means we'll have n minus 1 and has R vertices of degree, R minus 1, because we'll have removed 1 from each of these by deleting V sub 1. And the remaining vertices each have degree R. So have degree R. How many remaining vertices are there? Remaining vertices, there are n minus 1 minus R vertices. Each have degree R. And so how do we obtain G? So construct G. Construct G by adding the vertex V1 and having it adjacent to each of the R vertices of degree R minus 1. That will ensure then that every vertex has degree R, right? So these degree R minus 1 vertices, what we're saying is these must have been the vertices that were adjacent to V1. And the remaining ones were not adjacent to V1. And so just attaching V1 to these vertices produces the graph G. And that's it. So regular graphs are all recognizable, or rather reconstructable. All right, so another property that's recognizable is connectedness. So that is, we can determine if a graph is connected by looking at its vertex-deleted subgraphs. And so how can we tell? So in particular, graph G, G is connected if and only if at least two of the subgraphs G minus V sub I are connected. All right, so let's prove this. So let G be a connected graph. So if G is, so I want to prove first that if G is connected, then at least two of its vertex-deleted subgraphs are connected. Let G be connected. Remember that if a graph is connected, there's at least two vertices that are not cut vertices, right? Because then there's a spanning tree, and every spanning tree has at least two leaves. So let G be a connected graph. No, just let G be connected, sorry. Be connected. Then G has at least two vertices that are not cut vertices. And so the result follows. Right, that is two of the vertex-deleted subgraphs will be connected because those we have the two non-cut vertices. All right, so now suppose G minus V1 and G minus V2 are connected, and I claim that G is connected. All right. Well, then we can look at V2 in G minus V1. In G minus V1, so that's a connected graph. V2 is connected to every vertex. So that would be each V sub I for, it's not connected to one, it is connected to itself. So for each, so I between less than or equal to I, less than or equal to N, it's connected to all of those vertices. We can't say it's connected to V1 yet because V1 is not in the picture, but it is connected to all the other ones since G minus V1 is connected. And then if we look at G minus V2, then V1 is connected to every vertex. So this would be V sub I, where we can't say it's connected to 2, so we could say 3, less than or equal to I, less than or equal to N. However, because the order is at least 3, since N is at least 3, V1 is connected to V3, which is connected to V2. Remember here that connected does not mean adjacent. Connected means there's some path between them. So it's very tempting to swap, to think those are synonyms of each other, connected and adjacent. So V1's connected to V3, which is connected to V2. V1 is connected to V2. So every pair of vertices is connected. And that's the proof. All right, so we'll finish this video up in a second. I just want to say one more property. This is Theorem 9.10. So I'm not going to prove this one. But actually, so not only is connectedness a recognizable property, so therefore disconnectedness would also be recognizable. In fact, more can be said. Disconnected graphs of order at least 3 are actually reconstructable. So we can not only determine that the original graph is disconnected, But if we can do that, we can reconstruct the graph from that. So far we've extended what we know of the reconstruction conjecture is that all regular graphs are reconstructible, and all disconnected graphs of order at least 3 are all reconstructible. So we have a big chunk out of the reconstruction conjecture to big infinite classes of graphs. However, there are many, many more graphs to look at to prove that it's reconstructible. Okay, that's it for this video. In the next video, we'll work through yet another example of determining a solution to a deck of vertex-deleted subgraphs. I'll see you there.